Bismillahirrahmanirrahim. I'm to start a new topic with you guys, and that is named as Diels Alder Reactions. They are very specific reactions, not applicable to all sort of reactants. Very specific reactants are required for such reactions. Those reactants are supposed to be, the one reactant is supposed to be somebody having at least two alkenes, and the other reactant is supposed to have at least one alkene. This dialkene is called diene, as it carries two double bonds. Similarly, this is called dienophile. So, for Diels Alder reactions, we need actually two reactants. The one should be an alkene having two double bonds. The other reactant is also supposed to be an alkene. In very specific language of this reaction, this word is called diene, the other one is called dienophile. What happens during the reaction? The double bond between these two carbons, it moves into this side. The pi electrons over here moved over here. Similarly, the pi electrons move here. So a new bond is generated between this and this carbon, between this and this carbon, and our new bond, double bond comes between carbon number 2 and the carbon number 3 in case of an alkene. So what happens then? Let's say you have this, as I've explained, this has moved this way, so we have a double bond here. Okay, this has moved from here to here. Let's say if we call the two electron this and this end, it has moved over here, so we have a double bond here. Similarly, this double bond between carbon and carbon, this has moved forward in this way to make a new bond. This carbon makes a bond with this carbon, so we will have this sort of product. This is a specific product. Such products are furnished by the Diels Alder reactions. What is this? It's a six-membered ring. Six-membered ring. You produce it using Diels Alder reactions. Until now, the reactions we have discussed, they do not produce a sort of a cyclic product out of the alicyclic reactants. Means that the alicyclic reactants, linear reactants, they do react with each other to give us cyclic products. So whenever we want to construct a six-membered ring, we need to perform Diels Alder reaction. However, all sort of reactants cannot be made to undergo reaction to produce six-membered ring. Only the reactants which can give us such cyclic products, they are supposed to be, one should be in diene, mean 1, 2, 3, 4 carbons having two bonds in double, single, double situation. The other should be a dienophile. They react together to give us products. We have an idea. The alkenes are of a number of types. Similarly, the dienophile could be of a number of types. So, wherever the requirements are fulfilled, such reactants could be made to react under these Alder conditions to produce the six-membered cyclic ring. Let's say this is a double bond. It could have something like that, some sort of an aldehyde or a ketone functionality. Similarly, this sort of an alkene, the carbon number 1, carbon number 2, carbon number 3, carbon number 4. Number 1 could have any sort of, let's say it could have a CH3 as a substituent. So there won't be an issue with the product. As I've told you, what is the requirement? The reaction between this carbon and this carbon, that is supposed to be the reaction centers, Similarly, this is to be moved from this, the double bond between this carbon moves here to here to construct a new bond with this carbon. This bond moves in this direction. Similarly, this moves forward to make a bond between these two bodies. So let me draw again for you guys. Let's say we have this one, and this is supposed to react with another, somebody having this sort of a product, reactant, sorry. So if it moves over here to here, so means it has moved here, moved from here to here. Similarly, this body has moved from here to here, so I can draw it here, and this body has moved from here to here, the carbon between these two. So this would look like the product. What is the same in between the last and this product? We have achieved the 6-membered ring. 1, 2, 3, 4, 5, 6-membered ring. Whatever the substituents are, they are not the matter. The substituent which are present at the alkene diene, they will remain at the diene. The substituent which are present at dienophile, they will remain present as such. No reaction at all at substituents. They will not participate in the reaction. In a bit simpler way, I will explain how they can influence the reaction, however they will not participate in the reaction. So Diels Alder reactions, where you need two things actually. Diels Alder reaction requires two things. One should be a diene, mean an alkene having two double bonds, and then the other reactant should be also an alkene having at least one double bond. Then they undergo the rearrangement of the double bonds in this way to give the cyclic products. So I've told you earlier, the alkenes in the form of dienes and dienophiles, they could be of a number of types, they could be of a number of different chemistries. I can explain a bit further. Let's say I've given you an alkene. It's in this fashion. Similarly, I've told you to have another double bond. That's double bond between carbon and the carbon. It's something like CH2, CH2. In a bit simpler way, for very convenience, we don't write so we just keep the double bond like this way, okay? So I hope so you do imagine what is the what has been represented by these two lanes, So this is how it could be. As I've told you, it could be something. It's still a dienophile. What is the requirement? We should have one double bond. What is this? Either it's a simpler one, either it carries some sort of, let's say it carries some sort of a substituents, CH3s, or it carries chloros, somewhere it carries, let's say, cyano group over here. So no issues at all. Whatever is present on it will not a problem for us. There is no issue with the substituents. If they are present, they can keep their position in the product as well. What has to be the participating in the reaction? It's going to be this double bond. It has to participate in the reaction. This double bond has to participate. Similarly, if we consider these alkenes which carries two double bonds, whatever the substituent, we have an idea, they carry 1, 2, 3, 4 carbons are around. Every carbon can have any different sort of a substituent. No issues. Let's say this carbon number 4 carries CH3. This carbon number 1 carries OH. The carbon number 2 and carbon number 3 carries some other substituent like you can put in cyano group, you can put it chloro. So all these substituents present at the diene and dienophile, they will not be a party directly in the reaction. They will remain present at the same carbons wherever they are. They will be remain on the same carbon in the products as well. No problems, no nucleophilic reaction, no electrophilic reactions from these substituents. What is to be in the fraction? Only this double bond over here and these two double bonds in the diene. They are going to be part of the reaction. They are to move to make the cyclic adduct. Whatever the next substituent, whatever the other substituent around the carbons, 4 carbons on this diene and the 2 carbons of dienophile, whatever they are, they will remain as such present in the product. Let me rewrite it in more convenient way so you can imagine the reactions. It's a double bond here. Here we have this sort of. So what happens? What has to be happen? As I've told you, this double bond has to move here. This has to move here. This has to move here. So no, here means it has to react with this carbon, not this one. This carbon of the double bond. It has to make the reaction with the double bond. Similarly, this this bond has to react with this carbon. This bond has to be found with this carbon. This carbon. Over here, this carbon and this carbon, they are the metals. These carbons, which are the substituent, they will not be a party. They will not be a part of the reaction. So what's going to happen then? So I can write, if it's OH, no problem. It carries CN. It carries chloro. It carries CH3 in this way. So I can write CH3. The other one carries CH3, the chloro, it carries CH3 and then carries cyanide. So what happens then? This moves here, so I can make the bond over here. This moves in this direction and this body moves in this direction. So CH3 just sit like that. So we have a 6-membered ring. We have a 6-membered ring over here. In this fashion, wherever the substituents were, they remain on their respective points of attachment. They are present at the same carbons. They are not moving away. They are not taking part into the reaction. No substitution, no elimination, no reduction, no additions. Means whatever they are, they remain in silent during the reaction and they remain on the same carbon wherever they were in the reactants. They will be present at the same carbon in the product. But the product is supposed to be a 6-membered, 1, 2, 3, 4, 5 and 6-membered a cyclic ring. You know, that's the requirement of the reactant for the Diels Alder reaction, and this is the product which is supposed to be the ultimate outcome of the Diels Alder reaction, a 6-membered cyclic ring. Why we perform Diels Alder reaction? We perform Diels Alder reaction under such conditions when we want cyclic product rings from those reactants which don't have rings. Means if your starting compound, they don't have rings, but you want to generate the ring in your product, then you need to perform Diels Alder reactions. Let me explain a bit about the nature of the substituent present on the Dynes and dienophiles and how they can influence the reaction. They can influence the reaction. They cannot take part in the reaction. Influence means either they can speed up the reaction or they can slow down the reaction. The product will be the same. If they accelerate the reaction, means the same product could have been achieved in 12 hours. If let's say some substituent would have the ability to accelerate the reaction, then the product would be achieved in 12 hours. If the substituent are of the other nature that this slows down the reaction, maybe that the same reaction could have taken 16, 17 hours. I mean, they could just slow down their reactivity. Their collision could be slowed down. They would not be colliding properly. That's why the reaction could slow down due to the presence of the substituents, smaller substituent, bigger substituents, donating, withdrawing. These are, I'm just going to explain those. So those substituents could influence the rate of the reaction. Either could accelerate or they can slow down, but they cannot take part in reaction, means they cannot undergo any substitution, reduction, this and that. So let me explain a bit more about the nature of the reactant, nature of the substituents present on dienes and dienophiles. I will write it as nature of substituents on diene as well as on dienophiles. Dienes as well as dienophiles both can have different substituents. How the nature of those substituents could influence the reactivity, Generally, there are 4 carbons, 1, 2, 3 and 4 carbon at least in the dienes. The carbons are supposed to carry electron donating groups should be present on dienes for to accelerate the reaction. As a rule, it has been observed that the alkenes, means the one who carries 2 double bonds, means the dienes in such reactions, they undergo reaction at a faster pace, at accelerated rate when they carry electron donating substituents. On the other hand, these bodies, they carry 2 carbons, 1 carbon, 2 carbons, so substituents can be present at these carbons. These substituents are supposed to be electron withdrawing groups. If the dienophile carries electron withdrawing group 1, a few carry electron withdrawing group 2, means they are going to participate in the reaction at faster pace. So as a rule, dienes should carry donadings, the dienophile should carry electron withdrawing groups for a reaction to happen at accelerated at a faster pace, So this is how it is supposed to be the nature of the substituents. We have an idea substitute are electron withdrawing, like they could be carbonyls, it could be a sort of a nitro group, it could be a cyano group, withdrawings, some sort of, esters, some sort of amides. They could be substituted at carbon number 1, they could be at the carbon number 2. Both carbons could get the substituents, which can influence the reactions. The withdrawings are supposed to be there. Similarly, dienes, they should carry electron donating groups. We have an idea about the electron donatings. Yes, chlorobromos, hydroxyls, to some extent ethyl methyls, they are the donating ones. Amines, yeah, etc. These are the groups which could act as donating groups. So the presence of donating group at dyene and the withdrawing at dienophile, it accelerates the reaction. It enhances the rate of reaction. The reaction without these groups may have happened in 12 hours. If the donating of this body and the withdrawing this body are parallel, the same reaction could happen in, let's say, in 8 or 6 hours, something like that. So a reduction in time will be is supposed to be there with the acceleration of the reaction rate, you know. So this is how the nature of the substituents do influence the Diels Alder reaction, but they cannot influence the product. The product is always supposed to be a cyclic 6-membered cyclic ring, you know. That's the ultimate outcome of this reaction, and this is what this reaction is adapted. Whenever you want to synthesize, whenever you want to produce a cyclic ring, you can go for Diels Alder reactions. Now let me explain again. The dynes, also dienophile, it could be of number of types. Let's say we need a double bond. It could be something like that. A dyene could be somebody like 5-membered ring. Yes, like 1, 2, 3, 4, 5. One could start from here. 1, 2, 3, 4, 5. It could be something like that. Still, it carries one double bond, you know. So it's a dienophile. Similarly, it could be something like that. It's a 4-membered ring with one double bond. Yes, it could be a dienophile. We can use it. Similarly, it can be a without cycle. I've told you it can have this sort of aldehydic arachidonic group. It can have another substitute on this side, or one can move beyond that. Let's say it can be this type of cycle, or let's say it can be something like that. A double bond is there. What is that? It's not an issue. Until unless you have a double bond, means you have a dienophile ready for the reaction. Whatever the next is not an issue for you guys. It can have 2 benzenes. It's a unknown compound. No problems. A double bond is there. Until unless one double bond is present, that body has to act as a dienophile, whatever the substituents are. It could be the other way around. The benzenes could be transformed. I can write it the other way. Let's say a double bond is here. I can write benzene on these sides. Better to write, get the other position then. Yes, it could be something. Better to write like benzene on this side and benzene on the other side. The alkenes are supposed to be in cis as well as in trans forms. Cis and trans. You would have heard about stereochemistry. 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 The presence of substituents. The presence of substituents in the space, that's called stereoisomerism. Let's say this is a carbon. It's a carbon. A substituent is attached to this one. It could be on the left or it could be on the right. Left or it could be on the right. But the substituent is on the same carbon. Let's say we have 2 carbons, carbon number 1, carbon number 2. 1 carbon and then the carbon number 2. The substituent is present on carbon number 1 in one compound. In other compound, the same substituent, let's say it's a chloro, it's present on carbon number 1, but this time it is on the left side. And in another compound, the same substituent in the same carbon, but it is present on the right side. So one where it is on the left, the other compound where it's on the right, both compounds will be called stereoisomers. Stereo means space. Movement of groups in the space. It moves from left to the right, not in the same compound. In one it is on the left, on the other it's on the right. But the compounds are both. You have compound number 1 where it is on, like it's this way. It's a one isomer. Okay, you have another bottle. You bring that bottle up. You look into the bottle. The molecules carries in that direction. So first molecule and the second molecule, such molecules are called stereoisomers because nothing has been changed. This group and this group in both compounds are the same. One is on the left, the other on the right. In one they are both on the same side. They are in the opposite side. The other molecule they are on the same side. So it's called cis and trans. So why cis and trans? Two substituents are there. One substitute, two substitute. One substitute, two substitute. If one, then it will not be cis trans. It will be called a stereoisomer. One is on the left, one on the right. This is how you call the stereochemistry, stereoisomers. So still it's a dienophile, sorry. Let's say we have this sort of a compound, carbon-carbon double bond. It could be something like that. As I've told you earlier, no problem, it's a double bond. Or you can move beyond that. You have two cyclic rings. But unless it carries one double bond here, it has to act as a dienophile. That is why apparently seems this reaction is not that general because its requirement is very limited. One should be a dyne, the other should be a dienophile. So only few dienophiles are available, so few only can react to give the product, but that's not the case. You can see a number of compounds carries double bonds, cyclic or linear chain. So they can be used as dienophiles. Similarly, what's about the dynes? They could be of many types as well. Let's say it's a simpler dyne. It could be something like that. Whatever there are, could be many substituents. There could be a benzene ring. There could be a benzene ring. No issues. What is the requirement? Single, double bond is present. So they can participate in Diels Alder reaction. That's the requirement. That's the ultimate requirement that can make the reaction to proceed under Diels Alder reaction. Similarly, the other carbons are available. As I've told you earlier, they could be made to carry the substituents. They can have the substituents. Yes, they can have the substituents, and those substituents will be present in the products as well. And those substituents will not take part in the reaction, though they can influence the reaction as per their nature, whether withdrawing, whether donating. As I've explained you earlier, this is how they could influence the reactions. Again, let's see few more examples of dynes. Let's say, yes, it could also carry some sort of substituents like it can have a aldehyde functionality, it could have a ketonic functionality, it could have a simple cyclic rings, or let's say you have another dynes over here, the carbon number 3, 1, 2, 3, it has some sort of a functionality, no problems, unless you have one double bond and two double bond. It will serve to act as a participant in Diels Alder reaction, I do hope you got the idea what are the Diels Alder reactions, how they proceed. The Diels Alder reactions require only two reactants. The one should be the one which carries a double bond. It is called dienophile. The others are supposed to be Dynes, the ones who carries at least two double bonds. There is a variety of Dynes, there is a variety of dienophiles. Apparently it seems the reaction has a very limited applications because, as I said at the start, the requirement is very simple. Not simple, actually limited. The one which carries two double bond and the one which carries one double bond. That's the requirement. Afterwards, I've shown you a number of Dynes and a number of dienophiles, a number of Dynes. They could participate in reactions and they come up in the reaction to give you a product which carries cyclic ring. So what is the importance? The importance is that, number one, it gives you cyclic product. Whenever there is no cycle, there is no ring in your starting materials. Ring means there is no ring in this area. These rings not under the consideration at the moment. Then you can react the Dyne and dienophile to give you the products, cyclic products. Secondly, the reactions are greener reactions. Green reactions. Eco-friendly reactions. Green reactions, eco-friendly reactions. Why? During the reaction, as we begin with, what happens? Movement of pi bonds gives us cyclic product. Nothing has been eliminated. Nothing has been eliminated. No byproduct. No substitution, no additions, no electrophilic, no nucleophilic reactions are involved. Only the movement of the pi electrons gives you a cyclic product. There is no byproduct formation, there are no chances of byproduct formations. Such reactions are called green reactions, eco-friendly reactions. So Diels Alder reactions is one of the, again, a subclass of the, I would recommend it as a greener reaction because the pericyclic reactions, only the movement of the rearrangement of the pi bonds gives you the cyclic product. No byproduct formation is involved in such reactions. They come under green reactions, and the main advantage is that you can generate a ring in the product, in a product in which the reactant does not carry any cycles. So this is the main advantage of this reaction. In the next lecture, inshallah, we will discuss about the stereochemistry aspect. As I've told you, the dienophiles could have cis substituents or trans substituents. Similarly, this is a Dyne, it could have cis or trans geometry. Their stereochemistry, how it is going to influence the product formation. If the substituents are cis over here or they're trans over here, how they will arrange themselves in the product. Though they will remain on the same carbons, they will not go away. However, they can change their position. Let's say, as I've told you, in the space they can move from left to the right. Whether they can or not, we will look into those. Okay, whether they will move from cis to trans or from trans to cis, whether it will happen or not, what will be the stereochemical influences of the substituents on the outcome of the Diels Alder reaction. That will be our next topic for discussion in next lecture, inshallah. So stay tuned. Please go through what I've said. So go through the PDF file I've shared with you guys through WhatsApp. So you can come up with any questions, any queries on WhatsApp. You can put the questions in comment area. Approach me through email. I would be happy to respond to you in shortest possible time, inshallah. Thank you very much. I do hope you get the basic concepts about the Diels Alder reaction. Very fascinating reactions for you guys. Thank you very much. Assalamu alaikum.